Today is our honor to have our dear colleague Frances to give the colloquium, and we are going to learn how putting together two fields of science can make great progress. So Frances is an experimentalist condensed matter, even if today she's going to talk about gravitational waves and their contribution to the field. She started her career, I go back a long time, I started from the origin, 1985. She was a PhD student at Stanford. I think you worked with Teja Ball, am I correct? She worked with Teja Ball, the very known condensed matter physicist who actually passed away a few years ago at the age of 100 and 102. And he kept working and going to the office every day. So it's really like a role model for everyone, an inspiration. So she did her PhD there, and then she moved to a postdoc at AT&T Bell Labs and became a professor in 1994 at UC San Diego. She stayed there for 10 years, and then we were very lucky to have her come here to Berkeley in 2004. And since 2004, she has helped grow this department, change the face of the department, and make the department what you see today. She served for many years as the chair of the physics department, and then she served as the dean of the College of Letters and Science. So her leadership has really been very important in getting us where we are today. And then, then she decided she had to move on to bigger things, but thanks God she's still here with us. And in 2020, she became the vice president for American Physical Society, and since 2022, she's now the president of the American Physical Society. This is impressive, but not as much as when you hear about her contribution to science in the field of condensed matter physics. She is very known for her work in amorphous materials, magnetic materials, and she has changed the way we look at the system. And in particular, in 2006, she was awarded from the American Physical Society the Kitley Award for discovery of new experimental technique. And in particular, she developed micro and nanocalorimeters, which today is applied to many fields and has contributed to understanding many fields, especially the field of quantum material and amorphous and magnetic system. So she's, as I say, the world leader in this field. And she was invited, because of her contribution, also to participate in a collaboration with LIGO. And so today we are going to hear her work, really bringing together these two fields. Well, if this is not all, Frances is a very strong advocate for outreach. She served, I believe, at the Lawrence Hall of Science before. Am I correct? Yes. And then now she's with the San Francisco Exploratorium. She's a faculty there, and she helped develop and think about the vision of the Exploratorium. And then as fun fact, Frances, I actually learned today that she's playing in a band with her sibling, and she loves outdoor activities, she loves hiking, and doing trips around the world. So we are very lucky to have here our speaker today, Frances. Welcome, and looking forward to your talk.
Just glad that it is back in person.
Yeah.
Okay, well, thank you, Alessandra. That was a lovely introduction and much appreciated. Okay, so I am going to tell you today about detecting gravitational waves, and in particular, how does condensed matter physics help with this process? So I'm going to start by telling you some about gravitational waves, and then the many things that had to go right to make that possible, and in particular, where I fit in, that I was asked to join because of some work I had done in condensed matter physics, and how that fits into sort of some big picture things that I'm interested in about how amorphous materials, and hopefully I'll help you see what I regard as the beauty rather than just the disorder that most people think of when they see amorphous materials. So, with no further ado, all right, so let's start by just running through the basics. So what is a gravitational wave? So let's start with, it is a ripple in space-time. It is generated by changing quadrupole moments, such as by two orbiting black holes or neutron stars or a spinning asymmetric object. Now I'm going to show you in a little while, there are many other sources of gravitational waves, but the particular detectors that we use right now, that's what they're set up to look for. So gravitational waves are in fact strains. And so what I'm showing here in this bottom picture that too. There. This bottom picture is what I mean by a strain field. So you start with a square grid, and then it distorts one way and then the other way. And so the asymmetry in those two directions is what we're going to be measuring. Now, that strain that I'm showing right there is, I don't know, maybe 50% or something like that. The strain levels that we're going to be detecting are parts in 10 to the 21. So in particular, we're going to do this with a length that is 4 kilometers long, and we're going to be looking for changes in that length that are 10 to the minus 19 meters. Okay, so that is a part in 10 to the 21, very roughly. And to be even more dramatic about it, 10 to the minus 19 meters is less than 1,000th of the diameter of a proton. Not of an atom, but of a proton. So that is the length scale, that is the change in the distance that we're going to be looking for between two mirror surfaces. On the face of it, that sounds impossible. Certainly when I first heard about it, I'm like, that's absurd. Nothing's even flat to that extent, but that's not true. And so the question is, how do we do this? And so we're going to do this by bouncing a laser beam at 1064 nanometers. That's for various reasons the chosen wavelength between two mirrors. And we're going to use what's called a Fabry-Perot-Michelson interferometry system to do this. The detector, so when a strain wave like this goes through, it is best to think of this like a microphone. It's more like a sound wave coming through. So people actually you've probably heard the chirp that it makes. So it is often translated into a sound wave. But it is more like detecting a sound wave going across than like a telescope. All right, so in fact, the way you may know this, that we have, there's a detector, one is up in Hanford, Washington, one is down in Livingston, Louisiana. And so the displacement between those two, much like a sound wave going past, you hear that it goes through one, and then at some time later, let's just say, goes past the other one. And the time scale of that difference allows you to triangulate which direction the waves are coming from. So as I said, more like a microphone. And so in that timing, so we actually need to have multiple detectors to really make this work. So LIGO consists of 2 such detectors, one in Hanford, one in Livingston. There's also Virgo now in Italy. There's another system, Kagra, that is coming online soon in Japan, and et cetera. And so having the more positions you can triangulate between, the better chances you will know which way it is happening in the sky. Okay, and so just to show you, here is a schematic of 2 inspiraling. And so as those two, those could be black holes, they could be neutron stars. As they rotate around each other, they give off gravitational waves. And those gravitational waves are, as like I said, they're strains in space-time. This is not shown with them collapsing, but the energy carried away by the gravitational waves is a key part of all of this. So for example, when a binary black hole system collapses, you might start with one being 10 solar masses and the other one being 20 solar masses, so combined that would be 30. You will end up, as they spiral in, they start giving off these gravitational waves. The amount of energy in there actually translates into a mass loss. So the combined system is smaller than the added up masses of the two. So instead of having 30, I will end up with like 28 or something like that. And that extra mass is gone off in gravitational waves. It's also gone off in particles and light, other things as well. But the gravitational waves are a big piece of the energy that is taken away. Okay, so as I said, there are many sources, and this is just a schematic of the whole thing. So the things that we've been talking about are the binary coalescences, black holes and neutron star binaries. They're here. So they show up, depending on how massive they are, is how fast they spiral in, and that in turn translates into what frequency we detect. But so we're detecting them sort of in this frequency range, in this sort of, let's just call it something around a hertz up to maybe 100 hertz. At still higher frequencies, we would expect to see supernova results and spinning neutron stars. We're not sensitive to those right now. At lower frequencies, we start seeing the supermassive black hole binaries that may exist out there. They would be at much lower frequencies because they're enormous, but it is expected that they exist. And then finally, you start getting into like cosmic string theory, relic radiation, things like that. So there is just like with electromagnetic waves, there's a huge range of gravitational waves and all these different frequencies are things one would like to measure. In order to do that, so where we are right now, we are focused on the ground interferometers, which are, like I just talked about, these the Hanford and Livingston ones here. And then there's LISA, which is a space-based detector that is being envisioned sometime in the future. You get into various other kinds of pulsar timing arrays and so forth. And then, you know, at some point you get all the way over here, you're in a completely different method of detection, which involves looking at the cosmic microwave background, which people here are doing to try and look for relic effects of gravitational waves. So there's just a huge range of physics and a huge range of detectors you would need to detect all these different things. Okay, so I want to show you an image of what this looks like. So we will start with a laser and a beam splitter, and the idea is that the two arms change, and then that's one of the chirps going past. Seen from a different angle, here's the actual interferometry pattern. They interfere, they hit a detector. That's when it's static. Now, as you start changing the length of these two arms, about here, you see the interference pattern changing. And then finally, what you have in the detector is just a photodiode. So it just detects, you know, a bright and dark thing at some frequency, and that's in the end what you look at. Okay, so here is a schematic and an actual photograph. This is the Livingston, Louisiana site. As I said, the idea is that we are going to bounce a laser between these. So here's the laser input, about a 20-watt laser, hits the beam splitter, one goes off that way, one goes off that way. We then have this 4-kilometer long beam, one going one oriented this way, one oriented this way. They're always at 90 degrees to each other. Doesn't have to be 90 degrees, but that is a convenient geometry given the strain field I just talked about. And so the idea is we start with this 20 watts. By the time we then have, this is called the power recycling system. We start with 20 watts. We end with what is now 100 kilowatts of circulating power. It's actually more like 200 kilowatts now of circulating power. They would like it to be 400 kilowatts of circulating power. And in the next the next set of runs, they're hoping to get up to 800 kilowatts of circulating power. So if you think about that, 800 kilowatts of circulating power, what are you going to use for the mirror? In particular, you are not going to use a piece of metal, because the absorption in a piece of metal at 800 kilowatts, I mean, it would be vaporized instantly. It would be vaporized long before we even got to 800 kilowatts of circulating power. So you cannot use a metal for a mirror. So what you use instead is a Bragg reflector. We're going to use, it's essentially a quarter wavelength system with a multi-layer of a high index layer and a low index layer. And each of them are perfectly transparent and not absorbing at all. So you have to have less than parts per million of absorption. And the whole goal is with this Bragg, you actually use a multi-layer. And as you've calculated in some of your optics classes, you can figure out what's the reflection and what's the transmission from any pair. If you have an index of refraction difference, how much gets transmitted and how much gets reflected. So the bigger the difference, the fewer the layers you need. Right now we're at about 60 layers total, 30 pairs, because the difference in index of refraction is about, we're working with like 1.5 and 2. So it's not that big a difference in index of refraction. And as I will talk about when we get to my own work, one of the things that people would like is that silicon is a very nice insulator, not great at 1064, we'll come back to that problem, but it is an insulator, and the index of refraction is quite high, it's more like 3. So that would be much better to have the high index layer be 3 instead of 2. It would enable you to use fewer layers, for example. So this is the bottom line of how this system works. As I said, the displacement out of the 4 kilometers, we're trying to measure at 10 to the minus 19 meters. We are going to 800 kilowatts of circulating power. These test masses are enormous. I mean, on the scale of optics things, they're sort of 30 centimeters around. They weigh about 40 kilograms right now. They're right now made out of very pure silica, SiO2, quenched silica glass. Very high purity, very low absorption. Again, you have to have the absorption less than parts per million or you'll vaporize the whole thing. So yeah, so okay, and then here is the worldwide sites. As I said, there's LIGO Hanford, LIGO Livingston across the United States, Virgo in Italy, something called Geo 600, which is in Germany, which is a test facility. It's actually a test facility in Caltech as well that is important to one of the future LIGO systems. And then there's a setup in Australia and in LIGO India. They're both working on coming online. Hopefully will come online soon. Oh, and I wanted to mention, the LIGO, what's called the LIGO Scientific Collaboration has about, at this point, 1,200 plus members, something like 80 plus institutions, 17 plus countries. And from 2018, I was asked to join LIGO. So I am actually LIGO Berkeley. There is, there are a couple of theorists here in particular who've been very involved with LIGO, but they have chosen not to be a member of LIGO. They have an MOU to enable them to get the LIGO data, but I am actually LIGO Berkeley. So I am the sole, I and my lab, the group of my grad students and postdoc and project scientists are LIGO Berkeley. So we're working on a logo at some point to represent that, but that has not happened yet. Okay, so a little bit of history. So LIGO has been in development for quite a long time. The first, what's called, the initial LIGO, I think it was called, was not really expected to detect anything and didn't detect anything. So that was good, I guess, that they didn't. It is astonishing the amount of effort that went into continuing to argue effectively with Congress to continue funding this, despite the initial non-observation. But very fortunately, LIGO Part 2 did detect something essentially immediately on turn on. They went up another couple of orders of magnitude in sensitivity, and basically as soon as everything locked in, they made the first detection. And so the first detection was in 2015, was a binary black hole merger, about 1 billion light years away from here. No, million light years away from here, sorry. And it was announced in 2016. That's the New York Times article announcing that detection. In one fell swoop, that detection verified, like Einstein's theory of relativity, that gravity did in fact there's just a whole series of predictions that were all verified in that very first detection. It was a remarkable thing. There are no free parameters in this. So you know the mass of the two objects, you know how far away they are. There are just no free parameters. And so it's a sort of remarkable thing. It all worked. The signal was exactly what it was supposed to be and verified all sorts of fundamental physics with that. The Nobel Prize waited 1 year. We actually had Ray Weiss visiting here when not when they made the first detection, that was 2015, but in 2006, right before the Nobel Prize, Ray Weiss was visiting here and MIT was going nuts. They needed him back home because the theory was they were gonna win the Nobel Prize that year. And he, to his credit, just said, I'm sorry, I don't know if we're gonna win the Nobel Prize. So he stayed and gave the Segre lecture, I think it was. And so that was remarkable. I got to sit next to Ray Weiss while MIT was, his phone was literally, you have to come back here. We cannot have you in Berkeley if you win the Nobel Prize. So he stayed and they didn't win it. It was actually in 2017, by which time the Nobel Prize does not like to announce something and then have to take it back for obvious reasons. So there had been several more detections by the time they actually announced it. And one of the more interesting things that I got to experience, because by 2018 I was part of LIGO, so I was at the first LIGO meeting after the Nobel Prize. And it is heartwarming to listen to this collaboration. There are times when science can seem very competitive and people take credit whether they deserve it or they don't. The three people who won the Nobel Prize, Ray Weiss, Kip Thorne, and Barry Barish, two of them were there, one was not, one was not able to come. Everybody's on a first name basis with them. This is this huge collaboration with technicians and students and undergraduates and everybody from people who don't know any physics at all but know a lot about vibration isolation. And everybody was on a first name basis. The three of them tried to tell the Nobel Committee that the prize had to be given to the collaboration, not to the three of them. And the Nobel Prize Committee said, well, sorry, but that's not the rules. The rules are it goes to three people. So you can decline it if you wish, but you cannot give it to the collaboration. So they were persuaded that it was better to accept the Nobel Prize than to give it back. But they I heard them repeatedly saying, this is owed to the whole collaboration. And I've never been in such an experience of everybody being on this first name basis and just spilling over with giving credit to everyone else. The NSF person who had funded a lot of it was there also, and lots of credit was given to her for her efforts in keeping this funded. It was an amazing experience, and I felt very privileged to witness that. Funny font, but that's okay. So a couple of notable events. This one with what's called GW 170817, which is a nomenclature for the date, was two colliding neutron stars. The remarkable thing about two colliding neutron stars as opposed to two colliding black holes is that two neutron stars can give off tons of electromagnetic radiation and do. So two black holes, the black holes themselves don't give off light, and so there is much less that you can detect in the electromagnetic spectrum. But this colliding neutron stars, everything was sort of positioned right, that some detectors were actually pointing towards it, so they made it a whole series of remarkable detections of electromagnetic waves. They were actually able to watch the inspiraling and all the subsequent things. And one of the interesting things which has direct impact on Berkeley is we had theorists here who predicted, Elliott Quadrant and Dan Kaysen were involved in predicting, this is called a kilonova, and predicting what you would see in the event of a kilonova. And in particular, it explains what I had not realized was not yet explained, but apparently quite a lot of the periodic table of the heavy elements, such as gold and platinum, for example, I naively had always thought, oh, those come from supernovas. I thought everything came, everything beyond hydrogen and helium, I naively thought I had heard from Carl Sagan came from supernovas. But that's not true. There was actually not a good explanation for where gold, platinum, and quite a few other elements came from. And Dan and Elliott from Berkeley had a great deal to do with explaining where all these other elements come from. So that was a remarkable event. And there've been a couple of them. It's a big deal when there's two neutron stars because there is so much ancillary experiments you can do. So to date, there have been something like 10 black holes, 2 neutron star, and 2 black hole neutron star combinations. This is captured in this sort of a diagram, which they like to show. So what this is showing is, you'll see they're all in threes. That's because there's a binary at the bottom of 2 small ones, and then they combine together to make the thing at the top, and that, as I said, there's a mass given off in the gravitational waves and other forms. So that is not the sum of the 2 masses, but that is the arranged in time spectrum what has been observed so far of these binary systems. Okay, so where are we right now? So there was the initial LIGO, which made no observations. Then we went into what's called advanced LIGO, which is where all the observations you've heard about. But even within advanced LIGO, there have been these observations. So observation 1 was back in 2015. That's when the first were observed. Then there was observation era 2. And in between each of these, there's calibrations and there's upgrades and things like that. So 02 was 2017 to 19 roughly. And then 03 started up and barely had started up in 2020 when, guess what? COVID. And COVID, I don't think people thought it would, but it did. It shut down the observatories. It shut down almost everything. So the world shut down, including the observatories. So 03 was a very abbreviated thing, came back online. and was finished. And so we finished '03 about a year or so ago, and we're just getting set up for '04. And '04 is going to have a bunch more upgrades, and '04 is starting in May. So in May, you should start hearing, they're commissioning right now, which means it is possible that you will hear things even before then. There's a lot of effort that goes into thinking about what you do. You know, for example, there are really three. There's Hanford, Livingston, and Virgo are all coming online. Kagra is getting, the Japanese one is close to online, but it's complicated. It's a cryogenic system. It's the only cryogenic one in the bunch. There's a lot of advantages to cryogenic. There's a lot of disadvantages, not least of which is condensation. At one point they were getting, oh my God, it was something horrible, like 17 microns of frozen water a day condensing on their mirrors. And remember I told you you have to have low absorption and things like that? So it's a problem. The cryogenics, a lot of advantages, but there's a lot of extra technology that has challenged Kagra. But the bottom line is when '04 comes on, we're going to be out to something like 190 megaparsecs. There's been some significant additional improvements to LIGO that is extending the range. So far, this is all in those 4-kilometer lines. I'll talk a little bit later about where it's heading next, but the 4-kilometer lines. And so there's something like 1 million galaxies where we should expect to be able to see the neutron star coalescences. So there will be lots of events. '04 will have lots of events, and there should start being some real statistics and et cetera. So everybody's working very hard to get them up and going. And they may not all come on at the same time. Right now there's a lot of locking of lasers and quantum squeezing and just tons of things that all have to get done before they can come online. And so it's quite possible that like one observatory will come online before another. And then there's a lot of thought that has to go into, well, do you announce a detection if it's only seen in one? And generally speaking, the answer to that is no. There's too many glitches. There's too many things that can go wrong. If you only see an event in one detector, they don't like to announce it. They like that coincidence of seeing in 2, and better still in 3. There's quite a few. So I forget how many, there's dozens more detected was the word I grabbed. So there's dozens more that are detected that may well be events. One of the other interesting things comes up with, you know, the increasing emphasis on public release of data. Well, when? Do you publicly release the data before it's been verified, before it's been checked against the others? You know, what does that mean? And so there's a lot of thought that goes into when do they release the data? You know, a lot of people would love to get that data very quickly, but there's going to be a lot of false positives. Okay, so I wanted to start talking now about the major sources of noise, and that is going to lead me into, you know, what does condensed matter have to say about all this? So this is just a nice schematic of the system. It's got the same idea. There's the laser, there's the beam splitter, there's the 2 arms. And so the dominant sources of noise, these are the test masses, are first of all seismic vibrations. They're a huge range of frequencies. And remember, you're detecting 10 to the minus 19 displacements. So a huge amount of work has gone into all both active and passive vibration isolations of these things. So they're hung from almost impossibly thin fibers, the final test masses. And then there's all sorts of vibration damping and isolation. It's quite remarkable. Residual gas, these are all have to be in ultra-high vacuum. It's, I think, the world's largest ultra-high vacuum tube. I think it's bigger than CERN because it's physically, the beam, I mean, so the test masses are like 30 centimeters. And so they have to be, so the beam is actually an appreciable fraction of that. I'll show you the actual size later. But so the vacuum tube, that laser cannot be interacting, the 1/E of the light cannot be anywhere near the walls. And so if there's any gas in there, so it's a huge ultra-high vacuum chamber, the whole length of that 4 kilometers. And I think you saw it actually when we saw the newspaper article, they showed them in there like installing things, and it was the size of a human being. So it's enormous. So this has to be ultra-high vacuum, there's random phase fluctuations. Vacuum state field shot noise, that's one of the big ones, is the shot noise, the photon fluctuations. Radiation pressure, again, photon fluctuations. These are all things that they've beaten down. One of the big installations in 2019 was quantum squeezing of light. So that's all, there's a quantum squeeze, light squeezing has been implemented. They are now doing something which I think some of the laser folks in this room understand more than I do. It's called frequency squeezing of light. And so it enables them to push the squeezed light is mostly a high frequency thing, but they've pushed it down to like 50 hertz or so, or maybe even lower, using something called frequency squeezing. Again, I hope maybe one of the, if somebody wants to ask that question, hopefully one of the laser experts in the room can help answer that, because I'm not sure I understand what frequency squeezing is. So the thing I'm going to be talking about is what's called the thermodynamic mirror surface fluctuations, because that's where condensed matter physics comes in. And I will come back to what I mean by that, but for right now, that is actually one of the leading sources of noise, and also has been one of the most resistant to improvement. We have improved it, but it's been challenging. So this is a picture of a test mass. And so this is a picture right here. There's this, that is the 30 centimeter diameter. What you may notice in looking at it is it looks like it's reflecting, which it is, that is a good thing, but you can also see through it. So it is transmitting at any angle other than perpendicular. And then, but you see reflections off of it. And so you're seeing reflections off the front, back, et cetera, et cetera. So that's what this looks like visually. They're 34 centimeters in diameter. They're 20 centimeters thick. They weigh 40 kilograms. And the beam size, the laser beam size is spread out. You win with the area of the beam. So the laser beam is about 6 centimeters in diameter. I think that's diameter, yes. So, and in the end, this helps with, as I've noted here, insensitive to photon pressure from high power. That helps with the heavy mirrors. The large mirrors, you increase the spot size, so you average over more surface area. All these are part of how you get to that 10 to the minus 19 sensitivity. So just because it's so incredibly just amazing, this is the vibration isolation systems. There are something like 7 separate active and passive vibration isolations. The last stage, as I said, are these silica fibers, which are 600 millimeters long and 0.4 millimeter diameter. So they're tiny, and they're holding up these 40 kilogram masses, glued on the side, and even that glue is a problem. So you have to, there are teams of people that do nothing but worry about the glue, how you're going to attach those test masses to this silica fiber. There are teams of people who do nothing but worry about the silica fibers, because they can contribute to the noise. So every aspect of this has been, the noise has been beaten down and beaten down and beaten down to where this works. So it is quite a remarkable collaboration. Okay, so this is the plots that we look at all the time that show the sensitivity. And what this is the strain. So this is going to be the minimum that we can detect. So the strain that we can detect has to be above these lines. So the black line is the total noise. So obviously you have to have your signal above that. And then these are all the things that contribute. So all these various sources, they all have as a function of frequency. So each of the different sources has a different frequency dependence. And so, in here is the, for example, quantum fluctuations is the purple line, which is right there. You'll notice that that's not far off of the total noise. So that is one of the remaining, that is an important source of noise still. The one that is what's called mirror coating Brownian in here which is also sometimes called thermal noise. That's the thing that I'm working on. So the mirror coating Brownian is that red line, which is that line, which has a fairly simple frequency dependence, but you'll notice that it is a major contributor in that mid-frequency range, which we care a lot about. So this was the original LIGO up here, that dashed line. This is what's called advanced LIGO. That's where they got the first observations. We are now working on A+, which is A+ is what got implemented for observation run 3. And so, that is down here slightly below that. And the next one is going to be A#, which is all still part of advanced LIGO, but that's what they're aiming at for 05. So it's a constant matter of pushing whichever noise source is the dominant problem. And so the coding noise is the part of the that I'm involved in. And I mentioned quantum squeezing of light, so that reduced the frequency. That was a big contributor to improving the sensitivity. Okay, so I'm going to talk just a little bit about future LIGO, and then I will get back to what I do and how, because there's some really magic condensed matter physics that's going to come in here in a second. So A+ is what we're working on now. As I said, May 2023 is the fourth observation run. We're hoping for improved coatings with lower thermal noise. That is not going to happen by May. So that part of it is just being delayed. So there is a plan for an improved coating, but it's challenging getting it implemented. So it's in progress still. This frequency-dependent squeezing is actually working. I heard a bunch of talks where people were super excited because they basically implemented it, and it's already working, and it's working better than they thought it was going to. So that part's working. Farther in the future, we have something called Voyager, which is intended to live in the 4-kilometer arms and be a cryogenic system. So a prototype is being set up at Caltech. I mentioned that one in particular because it is a cryogenic operation. It's designed to run at 120 Kelvin, and it's going to have large silicon test mass optics, which means it is going to be running not at 1064 nanometers, but at 1.5 or even 2 microns. 1.5 microns lasers exist. 2 micron lasers don't really exist. So in order to make silicon work, it's likely that we're going to have 2 micron lasers. Not just lasers, but quality, stable, et cetera. So that is something that is being worked on. And it is likely the material I work on is amorphous silicon. And so amorphous silicon is envisioned as it will be the high index layer for the cryogenic operation. That part's almost for sure. And actually, oddly enough, it doesn't even need much improvement compared to what we've already done, depending on what wavelength they pick. 20-year timescale, we're talking about what's called third generation, which is Cosmic Explorer in the United States or Einstein Telescope in Europe. They're going to be much longer, like 40-kilometer arm lengths. There's a lot of debate whether they're going to be cryogenic or room temperature. At the moment, it all seems to be leaning towards room temperature. It's a lot simpler. A lot of things you don't have to develop if you can live with room temperature. There's things you gain by going to cryogenic, but that's one of the things. That is a debate going on right now, and Einstein Telescope making other trade-offs, some of the same decision processes. So, yes, so that's where we are. Okay, so my group. We were proposed about 5 years ago to be part of LIGO, and very specifically to be part of the Center for Coatings Research, and it was specifically because of the work done in my lab on amorphous silicon. And so I'm going to show you that. Now, amorphous silicon is an interesting material because it is a moderately well-developed material. It's been known for quite a while. It's an interesting one because it's very easy to make by vapor deposition processes, which is what I do, but you actually can't quench it. If you make liquid silicon, it's rather like water. If you take liquid silicon and you cool it down, the liquid is actually denser than the crystalline phase. So like water, where the crystalline phase floats on top, right? Ice floats on top of water because it's less dense. So silicon has the same thing. So when you try and quench the liquid state into a glassy state, what happens is it just nucleates crystallites. The energy is too high and it doesn't remain amorphous. But by an interesting thing that has been known for quite a while, it's quite easy to make it by vapor deposition processes. And so there was a reason I was working on this, but it was not about LIGO. So, but we did discover that we could make enormously reduced noise material by sort of serendipity. We were looking at something else and discovered this. So what we're trying to do right now is improved optical coatings for A+, sort of 2 to 4 times reduced loss. And my particular contribution is to try and take advantage of what I've already done in amorphous silicon and see if I can expand it into some other even more useful materials. So let me tell you about that. And before I do that, I'm going to just a few things. As I said, there is advanced LIGO. There is the hope for the A+ and A sharp, and actually I should say A+ in here. The spectral noise for this thing is, there's an equation that captures pretty much everything you need to know about this noise. The spectral noise has a thermal component, 2kT. The frequency, it's inverse with frequency. Remember that line actually sloped down. That's that 1 over f slope. There is the thickness of the coating, total thickness of the coating, not of a single layer, but of the whole multi-layer. And then there is the laser beam radius squared. There's the Young's modulus of the, that is the Young's modulus of the film. And then there is the mechanical loss of the coating. So what is mechanical loss? The easiest way to think about mechanical loss is, you know, if you take the Q of a material, like if I take a perfect single crystal of silicon and I hit it with like a little ball peen hammer or something like that, it will ring. And crystalline silicon has a Q, a very, very high Q, so it will ring for a very long time without damping. So what is the Q? The Q is how quickly does it turn that coherent vibrational motion into the dissipated, the phonons and things like that. How quickly does it dissipate that? So a high Q is a low mechanical loss, and a low Q is correspondingly a high mechanical loss. And this is captured with this angle. It's it's captured with this phi. And so what we actually do is to measure the mechanical loss. Now you can't, what we actually do is take a very high Q silicon, I'll show you in a picture in a minute, but a piece of single crystal silicon which has a very high Q, you measure its Q, then you deposit the film on it, and that lowers the Q. It's not as simple as a subtraction, it's a loading process, but it, more or less, you remove, you can, from those two measurements, before and after depositing the sample, you measure the ring down before and after, and you can figure out what the Q of your film was. Okay, so right now, sorry? Wait, one time? Yeah, no, Y prime is the Young's modulus of the substrate. So it's, yes, not, it's actually, I should define that there. Thank you for asking that. Yeah, so it's that ratio is all about the ratio of the substrate to the film. And we do measure the Young's modulus. This ring down process actually, well, it doesn't give you, it gives you the shear modulus or it gives you one of the moduli, and then you can from that derive the others. Okay, so right now, what they're using is the low index material is silica, which has an index of 1.5. The high index is a sort of random material. It's titania-doped tantala. It's sort of random in the sense that nobody designed that material to be a low loss. It was chosen because it is something that people in the optics community use for a high index layer. And so that's what they've been using. The added titanium helps with its index of refraction, and they do a lot of annealing. It has to not crystallize. I didn't even mention scattering. You cannot have any scattering at all. So there can't be any nanocrystallites in there because they would lead to scattering. So in this multi-layer stack, it is known that the loss angle for the tantala is much worse than the silica. So the silica is an anomalously good material. I'll show you that in a minute. But the tantala is a problem. And so these losses, so now we get into the condensed matter physics. These losses are believed to be associated with what are called the universal low temperature glass properties. And those universal low temperature glass properties are about tiny motions of atoms in the amorphous structure. So if I have a perfect crystal, you can't really move, at low temperatures, you can't really move one atom or even a group of atoms. They're sort of all locked in place. But in an amorphous system, you can imagine moving like one or a few atoms sort of within that structure without destroying the structure. So this is something that was discovered back in the 80s, that there are that if you take amorphous materials, non-crystalline materials, glasses, those are all the same word basically. It was discovered back in the 80s that, let's just take the heat capacity as an example. If you remember your sort of senior year or so physics classes, if you ask what is the heat capacity of a solid material that has no free electrons, so we're only going to do the phonon part of this, you may remember it goes as T cubed. There's sort of a universal T cubed dependence, and the prefactor of that is the Debye temperature, which is directly related to like the sound velocity. So if you have a very stiff material, it will have a very high Debye temperature, and its T cubed will be relatively low, and vice versa. A very soft material, you'll have a low Debye temperature, a low sound velocity. and a high heat capacity. So that is, you can derive relatively easily for a crystalline system. What happens in an amorphous system? Well, one of the beliefs is that that should be true for amorphous also. Amorphous systems are perfectly happy to carry sound waves. That's a measurable statement. You can propagate sound waves, and they propagate without, similar to what they do in a crystalline system. And moreover, their sound velocity might be a little bit lower. They're often a little bit less dense, a little bit softer than a crystalline material, but they perfectly happily propagate sound waves. So, and the sound waves at low temperatures are long wavelengths. So since they are long wavelengths, it should not matter that the material is crystalline or amorphous. It just shouldn't make any difference. You're averaging over it. So this is much like the argument if I take a string. You all know, you've done experiments where you propagate waves along a string. That string is not some single crystal. It doesn't matter. It really doesn't matter. Sound waves propagate quite happily in non-crystalline materials. So it was believed that when you cool down an amorphous material, it should have a T-cubed law. So there was quite a bit of surprise when it didn't. There is a T-cubed dependence, but there is a linear T dependence also. And it is very hard to figure out why there is a linear T dependence to the heat capacity. And there's other associated, you get something similar, thermal conductivity, mechanical losses. Lots of other properties have these what are called anomalous glassy properties at low temperatures. And one of the breakthrough papers back in the 80s, mostly attributed to Bobby Pohl at Cornell, is that they all look the same. So this is a universal property that glasses have, this low temperature linear term in their heat capacity and corresponding other such properties. That is found in the mechanical loss as well. So let me now show you the next slide. So this is a rather famous plot. This is a plot of the internal friction, the thing I've been telling you about. I'm showing it as 1 over Q. So it's the losses. So it's 1 over the Q factor of the film, of a whole ton of materials on a log scale. This is log scale, that's log scale. On a log scale of a whole bunch of glasses. And they're all in this universal range. Like all these different materials. And in fact, this is an early plot. It's been extended. There's just, everything has losses that are up in this sort of 10 to the minus 3 to 10 to the minus 4. So this is referred to as the universal glassy range. And there is a beautiful theory for these, which I will show you in a moment. A beautiful theory, actually I will cut quickly to the chase on this because we're running out of time. But there is a beautiful theory that explains these modes and why it's a linear heat capacity. There is no theory that explains, or not really, there's some efforts at it to explain why it's universal. So you'll notice an interesting thing, which is silica. The universal range is not supposed to have anything to do with room temperature. This is supposed to be entirely a low temperature tunneling phenomenon. But there is a way in which it empirically also applies at room temperature. There is almost nothing that it lies outside that range except silica. So silica has this bizarre thing that it has this enormous dip, and it's deeper than this is even showing. It actually goes down. The better you make it, the deeper it goes. So that's called the universal glassy range. This is just, I'm showing a little bit about to remind you of the structure of silicon and the structure of silica, silicon. And let's see, I want to show you, well, I'll show you just, I need to introduce one more important idea here, which is the, what's called the energy landscape. And this energy landscape plots the energy on the y-axis, and then the x-axis is just a configuration. And so this is what the point of this is. If you take a bunch of atoms, just assume it's like silicon, single atom, so let's not worry about composition. There's the crystal energy. There is a unique crystal that has a low-lying energy state. You now imagine that this crystal, if I'm at high temperatures, I sample all these different states. Every time I cool down, I'm going to land at some minimum in here. All these other states are all the possible amorphous states that it can make. So there's many of them. Silicon, every time you cool down, will be in a different configuration, will have a different energy. I plot this on something where I'm put states that are near each other. I put near each other on this plot. So this coordination Z is really a made up idea, but so this is called the potential energy landscape. So the idea of this is, notice something about this. The crystalline state is entirely unique, but there's a low-lying glass state. That low-lying glass state is arguably as unique as the crystal state. There is one state in there that is lower than any of the other states for this glass. That is called the ideal glass, and it is unique. So what is its entropy? This is a mind-boggling concept, and is the one big one I hope I can get through to you. Its entropy is, well, arguably 0. It's the same as the crystal state. It is a unique state. I will show you that you can also talk about this thermodynamically as well. Now, what's called the tunneling level states, which I'm not going to show you, I'll just flash through a couple slides. The explanation of those low temperature glass properties lies in, you have states that you can either thermally activate over or you can tunnel between. And there was a theory developed for these tunneling level states where once you mix, of course, you mix, you divide, you create each individual state now becomes a pair of psi1 plus psi2 and a psi1 minus psi2. The energies are now mixed, and the splitting of those states is micro EV. Everything else in this energy diagram is sort of EV, or maybe milli-electron volts, but it's definitely not micro-electron volts. So the only way you can get to micro-electron volts for energy splittings is through this tunneling idea. So this was, and I show you sort of schematically, it's not tunneling of a single atom, it's tunneling of a whole group of atoms together. And so with that, you can explain those universal, you can explain that there is a low temperature glass set of problems, that there is a linear heat capacity, there is that mechanical loss has this plateau, all of that data you can explain. You can't explain why it's only one number, by the way. That is a serious weakness of this model. But you can explain a whole lot else. Okay, so with that, I already mentioned that the way we measure this is we have these beautiful, what are called double paddle oscillators. They're single crystal, they have incredibly high Q. They measure a pure shear mode, which is convenient, so we know exactly what mode we're exciting. You put the film on and you measure the Q. There's the pure DPO, there is with the sample at it. It's not literally a subtraction, but that's the idea. And out of that you get the film. And this is the work that got me the attention. So what this shows is if I grow amorphous silicon at room temperature, which is where most people grow it, I have an internal friction, mechanical loss, that is up here in this so-called universal range. Looks, so that's a very typical, there's the silica kind of curve, that's a very typical glass. There's the silicon curve, nothing remarkable about it. It's a little lower, but it's nothing remarkable. The remarkable thing is what happens when I grow it at elevated temperatures. So when I grow it instead at 400 centigrade, which is just before it starts to crystallize, it is unequivocally not crystalline, not nanocrystalline, not precursors, not crystalline. The loss is way down here, orders of magnitude below the universal range. That's the thing that caught everybody's eye because everybody's been trying to fight this, finding a material that would have low losses. I can make amorphous silicon, high index of refraction, really low losses, not quite as good at room temperature, which is what we care about, but even room temperature is a lot better than anything else that anybody's making. We've recently found a way of beating the absorption down quite a bit by using hydrogen during our growth, so even that we're making some progress on. So this is a new, and the whole idea is that in this energy landscape, if I think of it thermodynamically, so far I've described it as in configuration space, it's a unique state. You can also do this from the traditional thermodynamic, how do you get entropy from a thermodynamic cycle? You measure C over T and you integrate it. So you do this by you start in the crystal, up in the liquid state, and you cool it down, and then you go into the supercooled liquid state. And supercooled liquid is not the ground state, but that does not matter. You can still define entropy, enthalpy, heat capacity, everything in the supercooled liquid state quite happily. There's not even an argument about that. The glassy state, it's more challenging because you're out of equilibrium. But the supercooled liquid is not the ground state, but is a metastable state, which is fine. So you can measure and track the entropy. And what you find is that in some materials, You can follow the entropy down. You never get to the crystalline entropy, but you can get remarkably close, and it's a very short extrapolation. So thermodynamically, you could also say that it is possible to get very close to this ideal glass state, and you can show that through thermodynamic arguments on the entropy. So it is a remarkable statement that I think is one of the big points I hope to leave you with, is that amorphous materials, they're not crystalline, but they have their own underlying order. It's a short range order, it's a medium range order, it's not long range order, but it's also not nanocrystalline. Nanocrystalline is actually quite a bit higher in the energy landscape because of disorder at the boundaries. But it is a very ordered state in its own way. And that low entropy, my claim, and this is a speculation, if you go back to this energy landscape, that lowest lying state, there are no nearby states, almost by definition. There are no nearby states, so of course there's no tunneling states. So by making this ideal glass, that is why I've made a low tunneling level state system. There are no nearby states. So the hypothesis is that while liquid quenching, you always fall out of equilibrium. It's very hard to reach a low-lying state. But vapor deposition has this very unique feature of the surface. So when you're growing a film by vapor deposition, you can grow at a temperature a little bit below the glass transition temperature, where the liquid would long since have fallen out of equilibrium. You can be at that temperature a little bit below the glass transition and still have tons of surface mobility. So the atoms at the surface are able to equilibrate and find that low-lying state is the whole point. And by finding, and when they find that low-lying state, it is a higher density state, it is a lower energy state, it is a lower entropy state, and it has no tunneling states. So I will just flip through this. I have another diagram to show it, but we'll just keep going. Okay, so let me just, I want to cut to the, I'm going to cut to the last conclusion I wanted to, last slide and then conclusions. So we've done an interesting thing from the fundamental physics standpoint already, which is we are able to prepare amorphous silicon, not just in this low-lying state, but we can prepare it in a whole range of states. And we've done that. And when you prepare in a whole range of states, we end up with a range of atomic densities and this remarkable plot showing the Q, where it starts off very low, grows exponentially, and then saturates in that universal range. So it is possible that we have solved this problem of what is the universal range about. We believe it's about when there's enough of these tunneling states that they start interacting, and that stops them from continuing to grow. And just as a sort of tantalizing other feature, I'm going to put the heat capacity on here. I haven't talked about heat capacity at all, but the heat capacity is another way of getting at these tunneling level states. The red is still that Q. The heat capacity just keeps going up. So, you know, we believe that this is all to do with how, we believe we're heading at an improved version of the standard tunneling model that is going to enable us to say the states themselves continue to increase, but it's their interactions that cause them to limit in this range. Okay, and then I'll just leave you the fact that for LIGO, it's great that we understand this. They don't really care that much that we understand this, that they really care that we find materials that can work. We've already found that silica does not do this. So silica, we can do the same thing. We can change the density. It's got a nice range of densities and a nice range of tunnel level states, but not those 3 orders of magnitude. All of our silica is still up in this universal range. So where we are now from a physics standpoint is trying to understand what's the difference between silica and silicon. Why can we make this low-lying, low TLS, low entropy, low enthalpy state in silicon, but not in silica? And so at the moment, we have a bunch of experiments planned to try and investigate this in other materials. But I will leave you with the summary. So the summary of all this, future advances require lower loss, high index dielectrics, maybe amorphous silicon or maybe some fragile oxide. We believe there's a correlation with what's called the fragility. The low losses is linked to this ultra-stable, near-ideal, low-energy, low-entropy glass, which is enabled by high temperature growth of vapor deposition. Now, again, this was a little bit for the experts in the room, so I didn't have much chance to point to this, but there is a theory called the random first order transition theory of glass transitions, which give us at least a qualitative way of understanding what I've just said from a theoretical standpoint. It is clear that, so there's this Kautzmann temperature, this crisis where you have to be able to make the ideal glass. So, and I'll leave it with these there's the open questions that are still in front of me from LIGO's standpoint. They don't really care so much about why exactly all this is working, but I do have an NSF grant where the NSF does care, and hopefully the world does care about the underlying theory of why this is happening. LIGO would just be very happy if I found another material. So with that, thank you. Should I repeat the question? Did people hear it? Okay, I'll repeat it. Okay, so the question is the optical losses. So I mentioned them, but I didn't talk about them. And are they affected by the same sorts of things? So it's not so the optical range they're talking about is for them the laser. So it's 1064, 1.5 microns, 2 microns, which is all infrared. So it's not really, well, it's optical in the sense of infrared. You would think that this was incredibly well understood, but I guess one answer to that is it is, in that range, it is a lot dominated by things like impurities and multiphonons and things that are, well, that's pretty intrinsic, but there's a lot about impurities in there. And so I was surprised, given how important amorphous silicon is to things like photovoltaic cells, that there wasn't just an infinite literature on optical absorption. But there isn't. So what's interesting to me, I had anticipated that it would be all about the dangling bonds of amorphous silicon. And we measure the dangling bonds. That's a straightforward thing to measure. And adding hydrogen is well known to soak up dangling bonds. And it does that pretty well even. We can do various ways of hydrogen. But I think what is actually the more important factor, and we've got evidence of this from our we make these films both by E-beam and by sputtering, and there's a big plus to that because there's a lot of differences in structure in those two materials. It also led us to be able to say that we have materials that have exactly the same dangling bond density, but 2 orders of magnitude difference on optical absorption. So, and vice versa, things with the same optical absorption, but an order of magnitude or factor a lot different in dangling bonds. So our belief is it is not about the dangling bonds at all. The dangling bonds are incredibly important to electron transport, holes. If you're going to make a photovoltaic cell, you got to get electrons and holes to split apart. Our belief is actually, and this is really recent. We have in the process of writing these papers up and analyzing data. Hydrogen does a really interesting thing. It lowers the energy barrier to reconstruction. So the silicon, any place that there's a weak silicon-silicon bond, a hydrogen can come in and facilitate that bond reconstructing to be closer. And it's not even, it may even be that the hydrogen goes away. Like this may actually be acting as a catalyst because the amount of hydrogen is very small in the films and yet it is necessary. So we end up with films with like fractions of a % of hydrogen, but substantially reduced like bond angle disorder, local strains, things, the Raman peak, stuff like that. So, in this sub-gap absorption, it's all about defects in the structure, and bottom line is not very well understood. The intriguing thing, and so I'm interested that you asked the question, is there any relationship to the mechanical losses? Because we didn't think there would be. If anything, I thought the mechanical losses might get worse because we've just got hydrogen in there. It could be, who knows doing what, but moving around and leading to losses. It turns out that when we introduce hydrogen, they both go down. The optical absorption and the mechanical losses are both improved. And in this framework of it's helping the structure to be better bonded, maybe that makes sense. But that's sort of where we are right now, that it does. So I'm struck that you asked that question because we were not anticipating it helping both, but it seems to help both. Oh, where I'm talking about the correlation length up there. So, okay, so briefly, how do we measure them a couple of ways. So one, there is an equation that plateau region in the mechanical loss, where the mechanical loss have like a plateau, and then they often have like a thermally activated bump and stuff like that. Let's see if I can quickly show that. Yeah, okay, good enough. That's a perfectly good place to show it. So that flat region, that is part of the standard tunneling model. And in the standard tunneling model, we call that Q naught. For obvious reasons, it's the, it's the plateau. There actually is a lower temperature, more complex stuff that goes on at lower temperatures. So this is all about like relaxation processes and things in this standard tunneling model. But that plateau is proportional to the tunneling level states. Now, there are, I somewhere have that equation, I thought, but, well, I'm not going to find. Oh, yeah, there it is. There it is. That is actually the equation. So it's a fairly simple equation in the sense of, so that's P bar is the tunneling level state's density, which is a density in not real space, but in energy space. Rho is just the atomic density, that's easy. V is the sound velocity, that's easy. But there is this gamma, and gamma is known as the deformation potential. It is also the TLS phonon coupling parameter. Those are the same thing if you work through the math. They are the same thing, except that the deformation potential is actually something that happens at each TLS. So at each one of these sites that has two energy levels, if you strain them, you distort the atoms, and so you change the levels. That's the deformation potential. That's the change in the asymmetry of the potential wells with strain. If you think, what would you call the phonon coupling constant, like a TLS phonon coupling constant? That is a strain. So that's why it's the same thing. In the theories, that gamma is just assumed to be 1 eV. I mean, the literature on this is largely theoretical, is very little. So gamma is virtually never measured. It's assumed to be 1 eV, and if you talk to the theorists, they say, well, okay, so maybe it's not 1 eV, maybe it's 0.1 eV. We don't really know, but it doesn't really matter anyway, because none of this is really numbers. Our belief is that that's the place that this STM is falling apart. The standard tunneling model. It's a poor understanding of what happens. This really is it's specific to each TLS, so there's actually a distribution. And then if you think about a distribution, you're probably sampling different parts of it. So short answer, or medium short answer, long answer, we measure P bar by either that plateau, so the plateau, or by heat capacity. And the heat capacity gives you another number. You can get other numbers. There's dielectric losses. We've actually done lots of them. They don't link that well to each other, which is obviously also an indication that it's not well understood. But the heart of what we believe is happening, which is in that very last slide. So it's sort of buried, as I said, I was kind of rushing by there. We, from measuring the heat capacity and the internal friction, can derive gamma. And when you do that, first of all, it's not 1 eV. It's quite a bit below 1 eV, hence the comment, well, maybe it's 0.1 eV. But we've actually got numbers down at like, 0.01 eV. And it changes with how we grow it. So none of this is making a lot of sense. So, I think this is going to force a reconsideration of what this means.
All right, I would say we say thank you to Frances for taking time.
Thank you.